All right. Yeah, so I'm Ed, and with me I have Raja, who's just off stage, but he'll join up here in a little bit. I'm a software engineer at Anyscale. I'm one of the original creators of Ray, and also still one of the maintainers of Ray. And Raja is a product manager from Google Cloud. And today we're going to be telling you a little bit about how we're working to make Ray and Kubernetes work even better together and sort of come together as like the de facto stack for AI. So let's start by talking a little bit about each of these sort of leading open source standards. I'm sure that everyone in the audience is familiar with Kubernetes and Ray, but let's dive into a little bit of kind of the motivation behind each. So Kubernetes is really built for container orchestration. And beyond that, it's built for production. So it's focused around this idea of declarative infrastructure. It's very extensive and modular. You can plug in different controllers and basically orchestrate all of your applications. And it's very, very focused on production use cases, right? So reliability and safe upgrade paths, rollouts, rollbacks, all the stuff that platform engineers care about. And what this means is that it's become the open source standard for platform builders, not just for AI applications, but also for web services and other types of applications. And Ray, on the other hand, is focused on sort of a different problem set. Ray is very much Python native to its core. We have an API that is very familiar for Python developers and an ecosystem of libraries and integrations with the best-in-class tooling for machine learning, AI, and also many other things, such as just pandas and NumPy and other Python ecosystem. And Ray is also optimized for scale, but in sort of a different way, which is scaling up a single application and getting the most out of your hardware resources, especially when you use hardware accelerators like GPUs, and mix them in heterogeneous clusters. So this is, all of these benefits have made Ray emerge as sort of the open source standard for AI and ML practitioners. So when you put these two side by side, it really makes kind of a cohesive picture. And we're calling this the distributed operating system for AI and machine learning. So we really want Kubernetes and Ray to be complementary and come together to give you the best of both worlds of something that's hardened and reliable in production, but also gives you a great user experience and performance and scalability for building AI and ML applications. And on top of this, Google and Google Kubernetes Engine and Anyscale RayTurbo come together to build sort of an even better solution than what you can get purely in open source. So the talk today, we're going to have 4 components. So I just told you a little bit about the high-level motivation of how Ray and Kubernetes are coming together to make this operating system for AI. I'm going to dive a little bit deeper into the motivation behind Ray and why we see it as well suited to these types of applications. And then I'm going to hand it over to Raja, and he's going to talk about how GKE is the best Kubernetes offering for running AI applications. And then finally, I'll talk a little bit about some of the optimizations and features that we have in Anyscale's RayTurbo. So let's dive into a little bit more of the motivation behind Ray. So I've been giving talks like this for quite a long time. It's kind of hard to believe how long I've been talking about Ray and kind of using a similar talk track. But you can imagine that 6 years ago, it was a lot harder to convince people that like distributed systems were needed for AI. At that time, people were still talking about ImageNet. They had like a GPU under their desk. And for the most part, they didn't really imagine scaling out to hundreds or thousands of GPUs. But at this point, it's pretty clear that scaling up compute for AI workloads is really not optional. It's a requirement. And not only is it a requirement, but it's also very expensive. So just one concrete data point here is, for LLMs, it's significantly cheaper to self-host LLM models for inference. But at the same time, it can be challenging. And the majority of organizations that do self-host AI applications report underutilization of hardware, which with GPUs as expensive as they are, means that they're basically just burning money. And the reason why it's so hard to get good utilization and sort of get to production quickly is because AI is not just like one clean use case in a box. it often requires stitching together many different parts of the workflow and different libraries, and going all the way from like data, ETL, and curation to online and offline inference. And one of the things I like to highlight on this slide is that every single time I give this talk, which sometimes is every couple of months, I have to upgrade the logos that I have to change the logos that I have on this slide because some new library has come out, or maybe one of them fell out of favor. The most recent one is post-training has become a huge trend, which Robert mentioned in the keynote, and we're seeing a lot of post-training applications built on top of Ray. And that's a box that just basically didn't exist before. Right? So this landscape's changing all the time. It's really complicated. It's hard for any one person to figure this out. And it's even more difficult than that because it's not one person that needs to wrangle it. You also have to have different teams that have different areas of expertise and different motivations, and they need to piece together this whole complicated picture, which means that putting AI in production is not just a technical challenge, but it's really an organizational challenge. And a lot of the people that we work with report that it's often slow to get things into production. They feel unproductive, and applications are very expensive because it's hard to get good utilization. So we see Ray as the unified AI compute engine to address this problem. So Ray Core is sort of this narrow waist that gives you the ability to just distribute Python code to heterogeneous clusters of resources. And I'll dive a little bit into an API example in a couple of minutes. But on top of that, we also have libraries that are built into Ray for training, data processing, batch inference, online inference, reinforcement learning, and now post-training as well. And we have an integrated ecosystem of all the kind of latest and greatest tools for machine learning and AI that play very nicely together on top of Ray. What this means is you can take the picture on the previous slide, and you can really simplify it pretty dramatically because you have this underlying infrastructure that you can use to run all the stages of the ML lifecycle. And you can do it all with sort of the same tooling. And then Kubernetes also sort of slots nicely into this picture because it allows you to build a hardened platform for orchestrating all the different types of Ray applications, and also allows you to use the same platform for managing other applications like web serving or other non-AI applications. So this has led a lot of the sort of bleeding edge companies to rely on Ray for scaling their AI workloads. So one of the customers that we work closely with at Anyscale is called Runway. I'm not sure how many people are familiar with Runway, but they're one of the generative video model companies. So this is a screenshot from one of the videos that they have. They have a ton of really cool demo videos that I would recommend you check out. I don't really know what the context is, but there's like a goat flying through the city, I guess. That'll look pretty cool. And Runway was able to cut their development time. So basically, the time from when they start working on a new model, including like curating and generating data, to when the model is deployed to production, they were able to cut that down from a week to 1 day. And it was basically by migrating on top of Ray and realizing that picture that I showed of unifying all the different steps on top of one platform. And it's not just Runway. Ray is really emerging as the open source standard for AI and ML practitioners. A lot of companies from a variety of industries, a variety of sizes, are all standardizing AI ML infrastructure on top of Ray. So let's talk a little bit in a little bit more detail about why Ray is well suited to these types of workloads. The first is that, as I mentioned, it provides a sort of narrow waist Python API and gives these building blocks that can be used in order to build AI and ML applications at scale. And if you look at this, tasks, actors, distributed futures, and resource requirements, none of these are really that specific to AI or machine learning, right? There's nothing about backpropagation here. There's nothing about transformers. It's really just a simple, basically parallel programming model that integrates very, very well with the libraries that are used for machine learning. So let's walk through an example of what this might look like. So here I have sort of a toy example, but it's pretty illustrative. So imagine that you have this DAG of compute that you want to run. You have some kind of input data. You want to run it across one piece of code that runs on CPUs. It might be just like Pandas or NumPy. It might be XGBoost or some other model that runs best on CPU. And you also want to run it against some compute on GPUs. So this might be a deep learning model or an LLM. You can sort of fill in the gap or fill in the blank. And then finally, you want to combine the outputs in some way, maybe perform some business logic, maybe write it to external storage. So I think many of you, if you kind of squint at this, it probably looks a lot like some of the things that you do when building and deploying ML models. But while this example is quite simple and it's kind of a toy, it'll highlight some really key benefits of why I think Ray is well suited to AI. So the first is that you can express this with a Python native API. And not just this kind of simple DAG, but you can do many other types of workloads can be expressed using the same set of core primitives. It also lets you express heterogeneous resource requirements natively in the code. So you can easily have actor 1 on one pool of CPU instances, actor 2 on a different pool of GPU instances, and then maybe that task can run on either of them, or maybe it needs some other type of resource. And finally, each of the stages can be independently scaled and dynamically auto-scaled up and down, which is one of the most important parts of Ray for optimizing cost and utilization. So let's take a look at what this looks like with some actual code. So first, we define like a regular Python function and task, which will contain the code that will actually do the combining in the case of the task, or apply whatever compute that we wanted to in the case of the actor. You can imagine that in reality, you would probably be importing Torch or VLM or Hugging Face or any sort of ML library, and then making calls to it inside the code. And then when we want to instantiate each of these actors, we just instantiate the class as normal, except using .remote instead of a normal constructor. And we're able to pass resource requirements directly in the code. We're also working on extending this so it won't be just CPUs and GPUs, but also allow you to express more complicated requirements, like what types of instances you need, if it's allowed to run on Spot, things like that. And then finally, you can orchestrate the computation using a regular imperative Python API. So you can orchestrate these .remote calls together. Each one of them is asynchronous and eagerly starts executing. And in this case, it's this pretty simple graph. But you can imagine if you just add a for loop above line 11, all of a sudden you might be able to scale the same compute to thousands of GPUs, or a mixture of a huge number of CPU instances and GPU instances. So this, when running on top of Kubernetes using KubeRay and GKE, you're able to develop using this Python native and imperative API, test it locally, and then with one simple step, you can deploy it to your Kubernetes cluster and deploy to production and scale up to thousands of CPUs or thousands of GPUs. And if you think about it, this is really kind of a natural evolution on top of Kubernetes. So Kubernetes came out really with the motivation of fulfilling this like service-oriented architecture, right? So this is at the time when people were crazy about microservices, and you wanted everything to communicate via RPC, like gRPC or REST APIs. But this would be a really challenging way to actually build like end-to-end AI applications. Imagine if each stage in that small compute graph that I showed you had to be its own microservice, its own container, its own YAML file. It just really wouldn't cut it, especially for ML researchers and practitioners who want to be able to iterate really quickly. So Ray kind of provides this layer on top of Kubernetes that we like to call dynamic distributed applications. So it gives you this programmatic scaling API. It has dynamic scheduling and auto-scaling that are built directly into the programming model. And it's very much optimized for getting the most out of accelerators for AI and machine learning workloads. So we really see Ray as kind of a next step and kind of an evolution of Kubernetes, and we want these two to work together as well as possible. So to that end, Anyscale and Google are partnering to kind of improve the integrations between Ray and Kubernetes. And I'll give a few examples of concrete things that we're doing here. So the first is working towards supporting in-place pod resizing to dynamically scale up and down Ray pods within a Kubernetes node and basically give you the best possible utilization across all the applications running on your Kubernetes cluster. We're also working towards enabling resource isolation for tasks and actors inside the Ray pod so that you can get the same resource isolation semantics that you're used to with Kubernetes pods, but you can do it inside Ray applications. I mentioned this a little bit earlier, but we're also working on a label selector API that will allow you to express requirements in the Ray application, and then we'll sort of vertically integrate that all the way into the Kubernetes stack and place the right tasks and actors on the right types of pods without you having to stitch those things together yourself. And then finally, we're also working on improving native TPU support so that you can very easily run the same code on both GPUs and TPUs and use whatever hardware is available and whichever one gives you the best price performance. So now I'll hand it off to Raja, who's going to talk a little bit about GKE specifically. There you go.
Thank you. Cool. All right. So GKE actually turned 10 this year, Kubernetes 10 last year. And over the last 10 years, we've been working a lot with a number of customers. And it's been exciting to see how customers' requirements have evolved. Actually, Edward just mentioned this a little bit ago. Like when Kubernetes first started off, the idea of stateless and these microservices was really prevalent. And with the ongoing need for support for accelerators and AI/ML workloads, things started to change a lot. And so one of the things that we did, working with IP Rally and a number of the customers that you heard from earlier today, is really start to evolve GKE and Kubernetes even more to support stateful workloads, accelerators, and a number of things that happen at scale. And it's been exciting to be on that journey along the way. This is a great marketing slide talking about how much we're pushing the envelope in terms of the bar, in terms of the scale of our customers. And a number of them are doing some leading edge things with tens of thousands of accelerators per cluster. But one of the most important things as a result of this work that we've been doing and pushing the boundaries is what we've learned along the way from working with these customers to improve the usability, supportability, reliability of Kubernetes, and better make it enable to support AI accelerator workloads along the way too. And that's something that we've seen predominantly with Ray being a very prominent framework that customers choose to run on top of Kubernetes and GKE itself. And a lot of the things that we've learned along the way fit really nicely with where Ray is going towards itself. First of all, for most of our customers, they really care about getting performant, scalable, reliable Kubernetes. And having the ability to support 10 times larger cluster scale for those training workloads, 60% lower tail latency, and starting to improve that throughput has become really important for customers along the way. With the cost of accelerators and these workloads that they're running, it's important to get faster startup times. And so thinking about reference architectures, working with the community about all the different tools they need to bring together to better enable that becomes important along the way too. And there's some areas that we've been working and innovating there to support, like secondary boot disks and image streaming for model weights and faster startup times as well, to maximize that consumption of those accelerators that you have and reduce time waiting for load time that happens along the way too. And then obtainability, we've heard from customers, that matters a lot. It's no secret that getting the accelerators that you want when you want them has been a challenge. And as we've brought in more accelerators and we introduced new choice, it's become possible for us to provide options along the way so that when you're starting to think about those workloads you're deploying, enabling your data scientists along the way to use Ray and deploy those workloads on top of Kubernetes and specifically GKE, giving a set of options so that they can actually get it when they want to. Leveraging a couple things around shapes of machine types, we'll talk a little bit more about that along the way, as well as our dynamic workload scheduler so you can actually ask for it when you want it and get that with fallback. We've been thinking a little bit about that entire stack and what that looks like for customers as they're deploying these workloads on top of GCP itself, and bringing together all the services from certainly the compute side plus Kubernetes from a platform perspective, frameworks, as you see there on the right-hand side, along with all the choices for consumption that need to be present and available. And I think as we're working together with Anyscale, it starts to introduce a dynamic to those conversations and talking a little bit more about those data scientists and how we enable them, but while still giving the level of control necessary for the underlying infrastructure along the way. And so Kubernetes has been one of the primary ways that we've been actually working very closely with Anyscale in the past and expanding upon that going forward. And as we look to make Ray a little bit more native on top of Kubernetes and make that combination, the distributed OS for AI/ML, it really starts with Kubernetes underneath it. How we can start piping through from the Kubernetes layer to integrate and pass back the metrics and information to make it more operational, more scalable, and more usable for the customers, whether that's the infrastructure operator, your platform admins, or the data scientists themselves, passing the information where they need to have it so they can use it and make decisions. There's a lot more that's going to come along there. This is just a starting point for that, and this is one of the layers through which we're going to do so. One of those areas that we've been actually working pretty closely with Anyscale along the way has started off with label-based scheduling. And the idea behind that is be able to enable you to actually pair Ray label selectors with node selectors and node affinity rules for finer control along the way. This actually starts to pair up really nicely with some of those underlying infrastructure side of things that we're doing with GKE to start nuancing things out. Now, certainly starting to leverage some of those node affinity rules from a Kubernetes perspective. But then if we start looking at other features that we have available, we'll talk about in a few moments, like custom compute class, you can go a lot further along the way too. But before we get there, cost matters, and optimizing that matters a lot more. There's a couple different technologies we've been thinking about. We've started off with secondary boot disk to actually load your model weights, your models, speed up that time, and even as you scale out, being able to make a constant latency for load times throughout that entire process. We've also started looking at Riptide for image streaming and working in open source and with other customers too, about how do we start bringing that entire time frame from the ability to go load something and create all the way to having it ready to use and shrinking that down. It's no secret as you start looking across industry and starting to set up these things, it can take minutes. And as you scale up, that cost goes up tremendously. We're looking at ways of bringing that down to 25% of the current time. And when you pair that up with the efficiency that Anyscale offers with Ray and RayTurbo, it starts to get very powerful in terms of the overarching value proposition of how that comes together. Oops, I went the wrong way. Custom compute classes is something that's kind of interesting. I started getting into that a few moments ago with label selectors. Well, one of the things that gets really interesting as you start going down that pathway is that you start having the ability to pair up Ray's fallback strategy with GKE's fallback strategy. And that starts to manifest inside of custom compute classes. Fundamentally, custom compute classes is for enabling you to optimize your utilization and resilience as well, with GPU fallback options that you can declare along the way. And so part of this is certainly the ability to kind of define and fine-tune your consumption and make sure you're getting the most out of it and getting the size and shape of what you need for the workload that you actually have. But then we can also define GPU fallback. And so whether it's on the obtainability side and being able to schedule when you want a certain type, define an alternate options, or as you're going through the actual deployment process and the cluster's lifecycle itself, pairing this up also with Ray and what its fallback priority handling gives you a really powerful way to kind of marry together what your data scientists are doing and what their requirements are with what you can offer from the infrastructure side, kind of bringing that whole story together along the way. One thing that we also notice is that accelerator choice matters. NVIDIA is awesome, but we've also seen a lot of cases where TPUs are interesting for customers for their flexibility of shape, price performance, et cetera. And one of the things that we saw along the way as customers think about different types of training use cases that they have, as well as inference, they start to shift across the paradigm from where they start off on the training side and moving into the inference side of things too. And our goal is to provide a set of choices to actually enable all those different scenarios. As customers go through that journey, we've seen cases where Ray has been really awesome, and RayTurbo too, for making it easier for the data scientists to go through that journey, allowing the infrastructure operators, leadership to make the decisions around cost, making it so that the data scientists don't have to reason through all those different changes. We're going to be working together a lot more to see how we can make that a lot easier for you and your developers and data scientists to take advantage of those choices and options, leveraging the right accelerator to choices as they go through that entire journey from end to end. I'm going to turn it back to Ed here to wrap us up.
OK. Yeah, so we talked a little bit about Ray and Kubernetes and how they're playing together, and we also talked about how GKE is kind of a version of Kubernetes that's like optimized for AI workloads. So I also want to talk a little bit about some of the work that we're doing with Anyscale's RayTurbo, which is our optimized Ray runtime. So with RayTurbo, we're trying to offer an experience that is fully compatible with the Ray API. Which means that you're able to migrate from open source Ray to RayTurbo without having to change any of your code. And it also means that you're not locked into using RayTurbo. You can always run the same workload on both. We're working on full stack optimizations, and we're focused on basically like the key AI and ML workloads that we hear about from our customers. And finally, we're also using RayTurbo as sort of a proving ground for emerging features or experimental features that we're not quite sure if we want to release in open source and maintain them there. So let's dive into a couple of examples. So the first is we've been seeing a lot of Anyscale customers that are getting a huge amount of value out of Ray data, and specifically for batch inference type workloads. So on RayTurbo, Ray data is even faster for the time to first output because it has some optimizations around accelerated metadata fetching. For aggregations, which are often used for basically pre-processing or featurization for training ingest, or basically the same operations before performing inference on data inputs. These are made even more efficient in RayTurbo by implementing streaming operators out of the box. And finally, RayTurbo has some intelligent spot instance handling and job level checkpointing, which means if you lose the cluster for any reason, if the head node goes down or all of the spot instances get preempted, then it will be able to recover from where it left off and basically not have any wasted compute. And when you combine all these things together, one of the benchmarks we ran is basically applying Mistral 8x7b across, I don't remember exactly what the input data set size was, but combining all of these optimizations, it was 70% cheaper than running the same workload on open source Ray. In addition to Ray data, we also have a pretty strong focus on elastic training or on training workloads with Ray Train. So one of the RayTurbo features is called elastic training. And elastic training basically improves your ability to handle failures. So here I have this pretty cool diagram that I stole from one of my coworkers' blog posts. And you can see we have basically a world size of 3. So we have like 3 trainers that are running, and they're running on spot nodes. But if one of them gets evicted, then what happens by default in sort of most training setups is that you'll pause and wait until the replacement node is added back to the cluster. But that means that you have now 2 GPUs that are idle during this period. So with RayTurbo, we've implemented elastic training. So it will basically dynamically change the world size and allow you to continue training with the nodes that are still available in the cluster. And then once a new spot node is available, it will get added and scale back up to the full size. And this can provide up to 60% cost savings, especially if you're training on spot instances, which often have these kinds of disruptions. So like I said, we're focused a lot on full stack optimizations, things that go all the way from kind of the bare metal up to the library level. And I'm not going to read through this whole list, but we have tons of ideas and always interested in working with customer partners to optimize their workloads and get the best possible price performance. And as I mentioned at the very beginning of the talk, Anyscale and Google are partnering to make RayTurbo available on GKE and improve the performance and price performance as much as possible. So be on the lookout for even more exciting announcements in the rest of the year. And with that, I will say thank you. And I think we have just a little bit of time maybe for 1 or 2 questions.